Good morning all. My name is Sinu Ravi. I'm a research professor working in the Department of Chemical Engineering at Yonsei University. My supervisor is Professor Yang Sung Wei. So here I am presenting one of my research work. Its title is Amine-appended covalent organic triazine polymer for CO2 adsorption and conversion to cyclic carbonates. Global warming effect is generally caused by the excess emission of anthropogenic CO2 emission, and such anthropogenic CO2 emission is occurred by the excess use of fossil fuel. So as we know that CO2 emissions, this kind of issues are receiving widespread attention in the recent time. So CO2 emissions major contribution is generally by the petroleum industry. And there are so many countries which emit high level of CO2, and South Korea is part of it. So we must reduce this CO2 emission by the CO2 adsorption process. That's one good application. The next thing what we can do is the CO2 conversion into a value-added product. CO2 can be converted into several value-added products. One important application is cyclic carbonate synthesis. This reaction is a high atom economy, which means like we can able to get the high product selectivity. This reaction can undergo in mild reaction condition, and the reaction carrying out process is very simple. In addition, the cyclic carbonates have several applications. They can be used as aprotic solvents. They can be used as a monomer in the polycarbonate synthesis. They are used as electrolyte in the lithium and batteries, and they are also used in the viscosity reducer in the coloring in the cosmetic industries. So far there are so many porous organic polymers are reported for the CO2 adsorption as well as the conversion reactions. However, there is no triazine based material, the metal-free triazine based material which is reported for the CO2 adsorption as well as the conversion reactions. So taking these points in mind, so we have prepared these two catalysts using the monomer called 4,6-dichloro-1,3,5 triazine 2-amine. So we have treated this material under the brittle condition in presence of these two aromatic linkers called biphenyl and 1,3,5-triphenyl benzene, and they yielded CTP1NH2 and CTP2NH2 materials. So this schematic diagram shows the possibility of using the material for CO2 adsorption as well as for the conversion reaction. So the polymer material is characterized initially with the FTAR analysis. As we can see here, the stretching frequency for the C double bond C, C single bond N, and the C bond H are present both in the monomer as well as in the polymer. Meantime, the stretching frequency in the monomer, the CCl at 647, is disappeared in the polymer, which suggests that all these bonds are reacted and it forms as a polymer. So the synthesis is quite successful. So further, the chemical state of elements in the polymer is analyzed using the XPS analysis. So here, the C1s deconvolution shows two distinct peaks at 284.6 and 287.7 electron volt. The one at 284.6 could be ascribed to C double bond C and the C single bond C binding energies, and the one at 287.7 could be ascribed to C single bond N and C double bond N binding energies. Similarly, the N1s shows two distinct deconvoluted peaks at 398.5 and 400.1 electron volt. So the one at 398.5 could be ascribed to the free amine group in the triazine moiety. The one at 400 could be ascribed to the the ring in nitrogen or the tertiary domain. Further, the pore surface property of these two materials are analyzed using N2 adsorption desorption isotherm. Both these materials shows type 1 isotherm suggests that they have high level of microporosity, and the pore space distribution is calculated using the NLTFT method. As you can see, both are highly microporous, whereas CTP2 shows slight mesoporosity at 3.37 nanometer. And these two materials show the surface area of about 875 and 4387 meters square per gram. And meantime, the CTP1 material shows the nitrogen content of 16.24, and whereas the CTP2 has the nitrogen content of 12.45 millimole per gram. Further, the morphology of material is analyzed through the SEM EDS. As you can see here, both the material have the aggregated spherical kind of morphology with the body size of 1 to 2 micrometer. The EDS mapping suggests that they have the carbon, oxygen, and the carbon nitrogen as the major element. So the color intensity of this material shows that the CTP1 has the high nitrogen content compared to the CTP2, which is in good agreement with the elemental analysis. Further, the TEM analysis of the material suggests that these two materials have the high degree of microporosity, which is in good agreement with the nitrogen adsorption desorption isotherm. Further, we have tested the thermal stability of the material using the TCA. So we can see that the material is stable up to 320 degrees centigrade, and the chemical stability is analyzed by treating these the CTP1 two material treated under the aqueous medium at different pH conditions, such as pH 1, 7, and 14. And after the 36 hour of time scale, we have tested the FTIR, and it shows there is no change in the peak position and the intensity, suggests that the material is very much stable under this pH condition. Further, we have tested the single component adsorption isotherm at two different temperatures, 298 Kelvin and 273 Kelvin, for the three gases such as CO2, methane, and nitrogen. So here we can see this two material is very much selective for the CO2 capture. It is shows in the red line. The CTP1 shows steep adsorption at the initial range, whereas the CTP2 material shows high adsorption capacity at the high pressure rate. The steep adsorption at the initial range is because of the high nitrogen content, whereas the high absorption of CTP2 at the high pressure is because of its high surface area. And the material shows high absorption capacity at the 298 as well as the 273 Kelvin. As you can see, the CTP1 and CTP2 capacities are 119 and 134 at 298 Kelvin, and at 273 it is 187 and 224 milligram per gram. Further, this results also compared with the previous report and suggest that this CTP1 shows one of the highest value obtained so far. Meantime, we have also calculated the ISD selectivity and the QST value for the CO2 absorption. The ISD selectivity calculated over nitrogen. So as we can see, the CTP1 shows nearly 70 and the CTP2 shows nearly 60. Whereas the QST value for CO2 absorption for the CTP1 material is nearly 35, and for the CTP2 is nearly 30. So, and then we have tested the catalyst performance in the cyclic carbonate synthesis. Initially, the reaction performs without the catalyst and shows a negligible epoxide conversion. And in presence of the CTP1 catalyst, it shows less than 2% conversion. And in presence of CTP2, the conversion was nearly same. When we test the reaction in presence of tetrabutyl ammonium bromide, the conversion was 26% with 98% product selectivity. So when we test both catalysts together, and the conversion is drastically increased to 93% and with high product selectivity of 98%. And CTP also shows quite similar performance, and which shows 91% conversion with 99% product selectivity. Meantime, we have also tested a series of nucleophilic additive and their effect in the cyclo addition reaction, and eventually we found that the tetrabutyl ammonium bromide is quite good for this reaction compared to the other nucleophilic additive we tested. So using the CTP1NH2 as well as the tetrabutyl ammonium bromide, the further optimizations were carried out. So the catalyst loading was tested from 10 milligram to 15 milligram. As you can see, the conversion of epoxide increased linearly until the 40 milligram loading, and then it is become saturated. So the optimum amount is 40 milligram. Meantime, the tetrabutyl ammonium bromide loading tested from 0.5 mole percent to 2.5. We can see the conversion also increased here linearly from 0.5 to 2 mole percentage, and then it is saturated. So the optimum value here are the 40 milligram and 2 mole percentage of this tetrabutyl ammonium bromide. And then the reaction kinetics tested at 40 degree centigrade at this optimum catalyst amount. So with increasing time scale, the conversion increased. With the allowed reaction time of 36 hours, the maximum conversion we obtained for the CTP1 is 93%, with 98% in the product selectivity. Meantime, we have also tested the reaction kinetics at two other temperatures such as 80 degree and 60 degree. At 60 degree, the conversion reached maximum of 98% within 6 hours. At 80 degree, the conversion reached maximum 99% within 3 hours of reaction time. So the results also compared with the previous report, and the obtained results are quite good, and which is comparable with the many reports reported previously. And further, the reusability of catalyst is also tested. As you can see, the catalyst can be used minimum of 6 cycles. The reused catalyst is also tested by the FTIR and the BET analysis. The FTIR suggests no change in the chemical state of chemical nature of the polymer, as well as the BET surface area suggests there is no change in the pore structure of polymer material. And further, in order to check the scope of catalyst, we have tested the cyclic carbon synthesis for using the different epoxides, different terminal epoxide as well as terminal epoxide. So we can see here all the terminal epoxide yielded a good conversion with high selectivity. Only the internal epoxide such as the cyclohexene oxide shows a lower conversion. That is because of its high steric hindrance at this carbon position. And then we have also proposed a mechanism using the CTP1 material. We can see initially the epoxide can be able to interact with the amine sites of the polymer through the hydrogen bonding interaction. When we use the tetrabutyl ammonium bromide, nothing but the TBAB. So this can open the ring of epoxide because there is a bromine anion that can open this epoxide by attacking this beta carbon. So subsequently, this kind of intermediate will form. This alkoxide anion will further attack the carbocation of the CO2, which is absorbed by the triazine moiety. And further, when the bromine leaves, the cyclic covalent will give the product. And the CTP material will be involved in the next cycle. So these are the conclusions we have made for this work. So here we have prepared two kinds of polymer. that is CTP1 and CTP2 materials, and they were characterized using different analytical methods, and they have high thermal stability and the chemical stability. They show quite good CO2 absorption as well as the conversion reactions. So that's all. So if you have any questions, please.
Okay, the session is open for question and answer. Any questions? Okay, nice presentation. I have one question about the comparison of CTP1 and CTP2. You have shown us the different heat of absorption.
Yeah.
Right. So I was wondering about what makes such difference.
We hope the difference because of this nitrogen content in the material. Because if you see the CTP1 material, so we have used the biphenyl as an aromatic linker. So if you take this carbon content, in the end, the CTP1 has a high nitrogen content. When we have high nitrogen amount, so the absorption of CO2 is also high at that low pressure region. So that made the difference between these heat of absorption.
That means if you normalize the heat of absorption with the amount of nitrogen, then those CTP1 and CTP2 are equal in terms of heat of absorption. That's what I'm talking about.
Yeah, we expect so. The nitrogen difference gives that difference in the heat of absorption. Yeah.
Okay. If you don't have any other questions, then okay, please give a big hand to Dr. Lavin.